So in the previous sessions we have studied time response analysis for first order system as well as we have solved problem. In this session we will be doing time response analysis for second order system. So the second order system is basically a vibration system having input R of S omega n square divided by S into S plus 2 zeta omega n, and this is C of S. This is a unity feedback. This is second order system. If we solve this overall transfer function, C of S by R of S will be given by omega n square divided by S square plus 2 zeta omega n S divided by 1 plus omega n square divided by S square plus 2 zeta omega n S. So this is G of S divided by 1 plus G of S into H of S is unity here. So if we simplify this, we will get omega n square divided by S square plus 2 zeta omega n S plus omega n square. This is overall transfer function for the second order system, where omega n is natural frequency, so usually omega n is undamped natural frequency and zeta is damping ratio. So generally damping ratio is given by the ratio of actual damping coefficient to critical damping coefficient. Omega n is given by root of k by j. So these are the terminology we will be using in second order system, and we need to solve this equation. So denominator we need to solve. If we solve denominator q of s will be s square plus 2 zeta omega ns plus omega n square. This is called characteristic equation. So we have to solve characteristic equation. In other words, s square plus 2 zeta omega ns plus omega n square equal to 0. So if we solve this, 1 plus g of s h of s equal to 0, we will get roots. So if we solve this quadratic equation according to Sridhar's method, S12 will be equal to minus b. This is in the form of ax square plus bx plus c equal to 0. Here a is 1, b is 2 zeta omega n, c is omega n square. So if I write a formula, minus b plus or minus square root of b square minus 4ac divided by 2a. So minus b is minus 2 zeta omega n plus or minus square root of 2 zeta omega n whole square minus 4 into a is 1 into c is omega n square divided by 2. So I will simplify this expression, minus 2 zeta omega n plus or minus 2 2s are 4. I will take 4 common, root 4 into zeta omega n whole square minus omega n square divided by 2. So if I take constants, 2 will get cancels, minus zeta omega n plus or minus. If I simplify this, omega n square is common. I will take outside square root of zeta square minus 1. So S12. These are the roots of characteristic equation. So this value depends upon the value of zeta If zeta is equal to 0, it is undamped system. If zeta greater than 1, if this value is greater than 1, what happens? This root of value will be positive. We will get real and distinct, and this case is overdamped system. If zeta equal to 1, if zeta is equal to 1, again 1 minus 1 will be 0, square root of 0 is 0. The same thing, but we won't get imaginary here. Here we will get roots are real and equal, which is critically damped system. If zeta is less than 1, if the value of zeta is less than 1, you will get root of minus something. So root of minus is imaginary. So roots are imaginary or complex. This type of system is nothing but it is underdamped system. So these are the different equation we need to solve. If we solve characteristic equation, we will get different roots. The roots of characteristic equations will be the solution for this. After this, based on the roots of characteristic equation, we will substitute the values here. We will calculate what is C of S. Again, based on the input R of S, C of S is converted into C of t by inverse Laplace transformation. So if I plot all those things here, t versus c, when we say it is a root 0, so it will be like this. This is zeta is equal to 0. If zeta is equal to 1, this is a graph we will get. It is critically damped. If zeta will be equal less than 1, it will be like this. So these are the different graphs. If zeta is greater than 1, this is a graph. It is overdamped system. So these are the different characteristics of controlled output versus time for second order system. Let us derive the different cases time response analysis for second order input considering unit step input. So if we say second order system, this is a system with second order. This consists of omega n squared divided by s into s plus 2 zeta omega n. So if we take closed loop transfer function, so this is a closed loop transfer function for the second order system. And we need to know what is R of S. R of S is reference input signal. Here reference input signal for unit step input will be R of t will be equal to A. Therefore, if it is a unit, A will be equal to 1 because it is a unit. Therefore, R of t will be equal to 1. R of S, what is Laplace of 1? It is 1 by S. So, C of S will be equal to omega n square divided by S will be there because R of S will be sent here. So, S into S square plus 2 zeta omega n S plus omega n square. So, this is the controlled output signal C of S for second order system with unit step input. So this is the step input, and how to get the C of t? C of t is C of S will be equal to omega n square divided by S into S square plus 2 zeta omega n S plus omega n square. Again we have to solve this using partial fraction method. So this will be A by S plus BS plus C divided by S square plus 2 zeta omega ns plus omega n square. Again, solve this using partial fraction method. Again, put s is equal to 0, you will get one value and equate coefficients of s square and s. First, if you equate s is equal to 0, you will get one value, equate coefficient of s square, another value, equating coefficient of s, again another value. If we solve this, the value you will get a is equal to 1, b is equal to -1, c is equal to minus 2 zeta omega n. These are the values you will get when you solve the partial fraction. So what I will be using is, I will replace this c of s will be equal to, I will take this part, what is a? A is 1 by s. What is b? B is minus s minus 2 zeta omega n divided by s square plus 2 zeta omega ns plus omega n square. Again, what I will do is, I will split this into two parts, 1 by s minus s divided by s square plus 2 zeta omega ns plus omega n square minus 2 zeta omega n divided by s square plus 2 zeta omega ns plus omega n square. And in this expression, what I will do is, 2 zeta omega n, I will write zeta omega n plus zeta omega n. That means 2 will be written as 1 plus 1. So the same thing here, plus zeta omega n, since it is a minus, minus zeta omega n here. So minus zeta omega n. So these two will be equal to plus zeta omega n. So what I will basically doing is, I will try to express the terms in terms of simplified Laplace transformation functions. So basically I will try to express the whole equation in terms of Laplace of e to the power of at, or Laplace of cos at, or Laplace of sin at. Like that I will be expressing. So s square is there, omega n square is there. So denominator I will try to express as s square plus a square. A divided by s square plus a square. If you take inverse, sin at. Similarly, s divided by s square plus a square. Let us try to write this expression in terms of that. So 1 by s minus, I will be retaining the numerator, s plus zeta omega n divided by, I will try to express this x plus zeta omega n whole square. I will express this in terms of s plus zeta omega n whole square plus omega n square. So this is the expression I will be using. It is in the terms of s square plus a square, s plus zeta omega n whole square. It will be s square, a square plus b square plus 2ab. So this is the expression what I will get if I express that in terms of this. And also what I will do is, I will be using the term omega d. Omega d is damped natural frequency, which is given by square root of 1 minus zeta square into omega n. So wherever there is a omega n term, I can write omega d divided by square root of 1 minus zeta square. For simplified version, this I will write it as omega d, which is damped natural frequency. The same thing, if I write the expression in terms of this, s plus zeta omega n square as it is, this will be equal to omega n into square root of this. If I do square, then I will get omega square into 1 minus zeta square. So omega n plus zeta omega n square, these terms will get cancelled. I will be remaining with the same thing. Again, this also I will be expressing like min zeta omega d divided by s square s plus 2 zeta s plus zeta omega n whole square plus omega d square. So the same expression, and here since I have replaced omega n as omega d, it will be zeta divided by square root of 1 minus zeta square will be there here. So if I take Laplace inverse, C of s becomes C of t, Laplace of 1 by s is 1, or Laplace of 1 is 1 by s. So Laplace inverse of 1 by s is 1, and this will be like first shifting property in the Laplace transformation. It will be e to the power of minus zeta omega n t into this term s divided by s square plus a square. So for this it will be a cos a t. What is a here? Omega t minus the same expression e to the power of minus zeta omega n t into sine omega t with this term zeta divided by square root of 1 minus zeta square. Here again e to the power of is common. I will take 1 minus e to the power of minus zeta omega n t cos omega t minus sin omega t into zeta divided by square root of 1 minus zeta square. What I will do is I will simplify this and I will take LCM. Then C of t will be equal to 1 minus e to the power of minus zeta omega n t divided by 1 minus zeta square into square root of 1 minus zeta square. This term goes here into cos omega t minus zeta will be there, zeta sin omega t. So this is an expression for C of t. This can be further simplified, 1 minus e to the power of minus zeta omega n t divided by square root of 1 minus zeta square. This can be written in terms of sine of a plus b. So what I will do is sine of omega t plus phi. Phi is a phase angle. Phi can be written as tan inverse of square root of 1 minus zeta square divided by zeta. So this is an expression for C of t, controlled output variable for second order system with unit step input. So after getting C of t, we need to calculate what is the error. So error is nothing but E of t. E of t will be equal to R of t minus C of t. If I take what is the error in the system, R of t is 1 minus of this. So 1 will get cancels. Directly I will write e to the power of minus zeta omega n t divided by square root of 1 minus zeta square into sine of omega dt plus phi. So this term I will write it as phi. So this is an expression for error signal for second order system. If I write the graph, it is varying exponentially. So that means it will be like this. Initially you have an exponential graph, later which is reduced because of suitable damping, and this is the graph for second order system. You can calculate further what is a ESS of S, that is nothing but steady state error, ESS of infinity. If you calculate that, it will be 0. Again, this term you have to calculate. That calculation depends upon again the solving of sine omega t. So amplitude you have to solve. This is about second order system with unit step input. Here there will be a certain oscillations. After that it will be stable. That stable you have to maintain using omega t and phi. That is omega d is nothing but damped natural frequency, omega n into square root of 1 minus zeta square. So this is just an extension of this, and some of the simplification directly you can replace this term with phi here, or else what you can do, you can stop here, and by stopping here itself you can write what is the equation for error signal. This term will be common. And instead of this simplification, you can retain this only. This is about the first case what we have taken. The first case is underdamped system. That means zeta is less than 1 here. Since it is an underdamped, we have derived all those expressions. Let us solve the time response analysis of unit step input for undamped system. Undamped system is nothing but there is no damping in the system. The value of zeta will be equal to 0. Taking into the same expression, first we need to get what is the roots of characteristic equation. Here if we give 0, we will get s square plus omega n square equal to 0, s square is equal to minus omega n square, so s12 will be equal to plus or minus j into omega n. So these roots are imaginary here, so we need to solve this. So you will get omega n square divided by s square plus omega n whole square. So if we solve this using method of partial fraction, you will get the values a is equal to 1, b is equal to minus 1 and c is equal to 0. Substitute this again, you will get c of expression 1 by s minus s divided by s square plus omega n square. After that, apply Laplace inverse. If you apply Laplace inverse, c of s changes to c of t. C of t will be equal to Laplace inverse of 1 by s is 1 minus Laplace inverse of this term s divided by s square plus omega n square is nothing but it is cos omega n t. So this is the expression for c of t what you have got. After this, find out what is the error signal. Error signal is E of t. E of t will be R of t minus C of t. So what is R of t? R of t for unit step input is 1. So 1 minus of cos omega n t. So it will be cos omega n t. This is a error signal. Again, steady state error, if you calculate, that is Es of infinity. That means Es of infinity will be equal to limit of t tends to infinity E of t. If you substitute t as infinity, you will get cos infinity. The value of cos infinity is 1. So the steady state error for this type of undamped system will be equal to 1. Since it is a cosine function looks like this. So the graph will be t versus c of t. If you plot a graph from the cosine function, the graph will look like this. This is a graph for zeta is equal to 0, which is undamped system. Here there will be no vibration, only positive value will be there, and this is a steady state response you will get from this undamped system. So the next case, the time response analysis for the second order system for unit step input, the next case is critically damped system. So here zeta will be equal to 1. The condition here will be roots are real and equal. Let us check. If you give zeta is equal to 1 because it is critically damped, then let us see what is the expression. Here expression will be s square plus omega n s square plus 2 omega n s plus omega n square equal to 0. So zeta will be 1, everything will be there here. So this is in the form of a square plus 2ab plus b square. We can write s plus omega n whole square will be equal to 0. So if we solve this equation, S will be equal to omega n plus or minus omega n. That means here the roots will be repeated. Roots are real and repeated are equal. So when we have the case like this, let us rewrite what is C of S. C of S will be equal to, again R of S will be 1 by S, that will be continued throughout. What is the denominator? The only change here will be omega n square divided by S into, I will write S plus omega n whole square. If I write according to partial fraction, this term will be A by S plus B divided by S plus omega n plus C divided by S plus omega n whole square. The same thing by using partial fraction method and equating the coefficients. The value of A what you will get is 1, the value of B we will get is minus 1, and the value of C you will get minus omega n. So if I substitute here, C of S will be equal to 1 by S minus 1 divided by S plus omega n minus omega n divided by S plus omega n whole square. Apply Laplace inverse for this. If I apply Laplace inverse, C of S becomes C of t. Laplace inverse of 1 by S, that is nothing but 1, minus Laplace inverse of 1 divided by S plus omega n, 1 divided by S plus A, it is e to the power of minus at minus, this is very important here, omega n divided by S plus omega n whole square. There will be a confusion, directly will opt sin at. That is not the case here. Omega n, take that as a constant. Laplace of 1 by S square. Laplace of 1 by S square is nothing but it is t. Laplace inverse of 1 by S square is nothing but t. Then S changes to S plus omega n. That means it is a shifting property. So what we can write is it is a multiplication rule, t into e to the power of minus omega n t. This is a root of this. If I take e to the power of minus omega n t common, it will be 1 plus t into omega n. So this is C of t, that means controlled output signal for critically damped system. Again the same thing, I need to calculate error signal. Error signal is nothing but E of t. This will be there always. E of t will be equal to 1 R of t minus C of t. Directly I will write 1 minus of this. So minus into minus plus, 1 will get cancels. E to the power of minus omega n t into 1 plus omega n t. So this is error signal, and if you calculate what is steady state error, it will be 0. And then you can plot the graph. If you plot the graph, since it is varying linearly, it will stop here. This is value of zeta is equal to 1. This is a response of the system for second order with unit step input with the condition critically damped system. Let us take up the next case. It is a overdamped system where the value of zeta is greater than 1. So the steps will look like very bigger one here, but it is not so difficult. Here zeta is greater than 1 means you will get this as a positive. Here the roots are real and distinct. So you will get different roots. Those different roots are minus zeta omega n plus or minus omega n into square root of zeta square minus 1. If you get plus, it is S1. If you get minus, it is S2. Again, with the help of partial fractions method, if you solve, you will get C of S is equal to this. The same thing for underdamped system, what you have derived, the same case is for C of S. But here, there will be no imaginary part. This is a simplification of C of S. If you apply Laplace inverse, you will get this term, and here S1 and S2. S1 are nothing but minus zeta plus or minus square root of zeta plus 1. If it is plus, it is S1. If it is minus, it is S2. So these are the expressions. So it is just like deriving an underdamped equation. That's why directly I have written the equations. Then this is a response graph. If zeta is equal to 1, this graph will be constant for some time. If zeta is greater than 1, this will go increases. So this is not showing either steady state behavior nor transient behavior. Most of the systems, we are not using underdamped system into consideration. Sorry, overdamped system into consideration. We will take only one case, that is underdamped system, because it will be having positive and negative. There will be oscillations with respect to mean position. It will show both transient as well as steady state behavior. If you take this system, it is not showing any transient or steady state response. If you take zeta is equal to 1, it is also not showing any type of response. If you take zeta is equal to 0, undamped system, it is showing steady state, but that system we cannot take in practical consideration. We will take only one system, that is underdamped system. Thank you.